Hello, I'm William, and this is my Fluent 2 project. We're going to be calculating and simulating the boundary layer and velocities of an external flow over a flat plate. So the first thing we're going to do is open up a Fluent simulation. This will in our workbench here, and this will be the base for our simulation. So we're going to right-click on Geometry, and then click on New Design Modeler Geometry, and then wait for this to load. So since we want a 2D model, we're going to go ahead and click on the Z-axis, so that we're only looking at the Y and X-axis. And then I also went over to the settings and set the grid to show in 2D and snap. And for the major grid spacing, I set it to 0.1. Minor is 10 units per 100 centimeters. And then we're going to go to draw and then rectangle. And we're just going to start from the origin and then make it roughly 100 centimeters. And then we're going to go over to assign the dimensions. So we'll hit here, boom, boom, for our vertical and horizontal. So this bottom portion will represent the plate, the flat plate that we'll be using. This will be a boundary, and this will be another boundary for the air that will be moving over this plate, and then this will be the top boundary. So we're going to set the horizontal length to 100 meters or 100 centimeters. So we'll click on units, change it to centimeters. Horizontal to 100 centimeters, and then for our vertical, we're going to set it to, say, like 500 centimeters for now. Actually, we'll just do 100 for the height, since we only need to capture the velocity profile at 35 and 75 centimeters, so 100 should be okay. So we got this little square here. So now we're gonna create a surface from our sketch here. So we're gonna go to Concept and then Surface from Sketches. Make sure our sketch is selected, and then click on Apply, and then Generate. So this is our surface here. And that's pretty much it for our geometry. So we can go ahead and exit this, and we can see here that our geometry is checked off, and we can now work on our mesh. So right click Mesh and click Edit, and then wait for this to load. So now we're going to be changing our sizing for each boundary and the bottom wall, or flat plate. So we're going to go ahead and click on the Z to make it 2D. Then we're going to click on Mesh, Insert, Sizing, and then we're going to select, click this side, Apply, element size, change this to divisions, hard, bias, 60, and reverse this. Just do this. Oh, there we go. This is what we want. We want more measurements from that are closer to the flat plate, so that we can get better results. Looks good. Now we're going to click on insert sizing again and select this side. Click apply. Color divisions. Make it 70. Hard. Device. This. Yeah, there we go. This is what we want. That looks good. And then we're going to click on this again, insert sizing. We're going to select both the top and bottom. Apply. Number of divisions. Do 50 for this one. And then change the behavior to hard. Right. That looks good. And generate. Give it a second here. Select all these. And then click generate. Alright. Yes, this crucial step right here. We have to also insert a face meshing. And then click on the face, click apply. Okay. We can use quadrilaterals or triangles. It might look better. Yeah, that looks cooler. And then we're going to move on to our next step in the project since our mesh is done. The next step is to name our surfaces. We got the inlet, outlet, upper boundary, and then the flat plate. So this is our airflow. So we're going to go ahead and use section. Oh. So now it'll show up here our name selections. Now we're going to name our edges. Select here, press N. Inlets. Name this one outlet. Then we'll select our top edge. Call it. We'll call this one the far field pressure. And then for our bottom plate, we'll name it the bottom plate. Or just plate. This is only one plate. Good. This pretty much sums up what we have to do for meshing. We got our name selections and our edges. Everything looks good. Got this. Alright, so we can go ahead and close this out. And this will update. Just got update. That should show up as a check mark. Alright, that's good. We got our check mark, so now we can start setting up our parameters. So we can go ahead and edit. Solver process. I think this is a 12 core. double precision. Yeah, this looks good. Alright, we'll go ahead and start. It'll take a little bit to load, so we'll skip to when it's fully loaded. Our mesh is loaded into the simulator. We did a check on the mesh to make sure it looks good, and the mesh quality over here in the quality report. In our general, we want to make sure our solver is processing the right data. So we got pressure-based absolute velocity formulation. Our 2D space is planar, and we are doing H steady state simulation. And then we're gonna now move on to our parameters for, say, like our air type and our velocity flow and all that. So for our simulation, we're gonna have a steady, viscous, and laminar. So we're gonna change in our models tab here. We're gonna double click viscous and change this K omega to laminar. Click OK. Good, now we're in the laminar. So to set our parameters for our materials on medium here, we're going to go to fluid, air, and set this. We want our air density 1.2. Our viscosity is given as 1.8 times 10 to the negative 5. So we're going to go ahead and set these. Alright, let's go change, create, and then close. Now for our cell zone conditions, we're going to make sure our airflow is using air as our material. Now for our boundary conditions, we're going to go ahead and see our wall and select plate. Make sure it is a stationary wall with no slip condition. Looks good. Click apply, close. So we're gonna change our inlet boundary conditions to a different type. So we're gonna go ahead and let's see. Click on type and then click on velocity inlet. That was already selected. And then we're gonna go ahead and change our velocity magnitude to 2 meters per second. This looks good. Click apply and then close. So for our outlet boundary condition, we're gonna go ahead and double click. It is already set to a pressure outlet. So we're gonna see our what we got here. Gauge pressure 0. That's good. It's atmospheric. There's no delta P. No totality. Just do just for now, we're gonna go ahead and prevent the reverse flow. I'm not sure if it'll affect our results, but that's since we only have one inlet and one outlet. It should be fine. It's a simple simulation. So click apply, close, and then we're gonna go and touch far field pressure boundary. So we're going to change the type of this pressure far field to a symmetry. And then click apply. Close. So our boundary conditions are good. This can be kept as is. So for our methods, we'll set the scheme to simple. And then for our controls, we'll just keep these as they are. The one thing we want to change is the monitors. Double click on residuals. We'll do -6. -6, or just do 5. 5 should be good. Okay. So we'll go ahead and double click initialization. Primary initialization is good. Click on initialize. Hybrid initialization is good. Now we'll double click run calculation. For our number of iterations, we'll do just do 100,000 for our number of iterations, and we'll just sit here for a little bit. So click calculate. While it does this, we will come back to you. Oh, it's already done. Calculation's done. Now we can go to our results. So double click results, and then we'll begin processing our results. So to set up our results, click on the z-axis to get back to 2D. To create a contour for our velocity, so we're going to create a contour, and then we'll do location, field 1, velocity u, number of contours. That should be okay. That's good. So click apply. Then we'll be able to see our do airflow. No. It should be symmetry 1. Ah, there we go. So now if we zoom in a lot, we can see that very slightly our boundary layer for our velocity. This is the maximum velocity, and then this is our minimum velocity. It should be 0 right at the surface plate, and you can see it does increase gradually. The increase is more drastic at the beginning, so it goes to the maximum velocity on the higher y values, and then closer to the end we have a much, not much, but a longer distance to be covered to have to get to the maximum velocity away from the plate. But you can see it is a very gradual change. See over here, it's barely any y change for the change in velocity. I could reduce the geometry for my height, so I'm going to go ahead and do that, and I'll come back to those results. So I made the height of my geometry 30 and reran the simulation, and now you can see the boundary layer a little bit better. See that it starts from basically almost a 0 height to about here. The boundary layer is where there's a difference between the maximum velocity, which is 2 meters per second, and it goes barely below 2. So wherever that line is where our our boundary layer is you can see it's slowly increasing in height as we get further along, and it's a little bit more clear now when I change the velocity. So now if we want to see our vectors, go here, double click vector. Looks good. Display. And now we can see our velocity vectors like this. So we can see we got a little bit longer distance to cover to get to maximum velocity than compared to here, where it's barely anything. So these look like good results. We have to set our velocity lines so that we can see our velocities at 75 and 35. Location, line, just call it line 1. Point. Alright, so we got our line parameters right. Yeah, Alright, so this is right. After clicking apply with these domains, we'll click on chart right here, and then for the data series, we're going to set this to x equals 75 centimeters, location line 1, and then for the x-axis we're going to do velocity u, y-axis we're going to do y. Then we'll click on, we'll add another line, so location line 2, okay. And then for this line, we're gonna do 0.35 meters. 5 meters. Samples 50. Apply. So in our chart, double click here. We're gonna add another data series for 35 centimeters. Location line 2. X-axis, velocity u, y, good, apply. And now we get this. Alright, so we got our line parameters right. Yeah, I just had it in the wrong power of 10. So now we can see our lines here are in the right spots. So when we check out our chart, we get this data, which looks a lot better, more similar to the one I saw in the video. You can see that there is a slowly increasing velocity, our boundary layer, which I guess is, just looking at it, our boundary layer shows up here. So if this is our height, and okay, this makes sense. Calculated boundary layer thickness, we get 0.0137 meters. You can see here that at 0.0137 meters, it cuts off right here and then goes to a maximum velocity at 0.0137 meters. So that lines up with our results, and that shows we have a valid simulation. So in order to have our blousiest theoretical answer for our boundary layer, we're going to go back to the here at the solution page, and we're going to click on XY plot, and then change our plot direction for x from 1 to 0 and then y from 0 to 1. Change our x-axis function to x velocity. There we go. We gotta position it to the y-axis. I just did this. So for this one, this has direction vector. For the x, we're gonna put velocity. Change this to x velocity. And then for our surfaces, we're going to select outlet. Only outlet. This finishes setting it up, so click Save Plot. We should get this. Okay. So in order to get our skin friction coefficient, we went over to XY plot, double click that, select the position on x-axis, plot direction 1 on x, 0 on y. We set the y function to wall fluxes and then skin friction coefficient. And then we selected the plate as our surface, and that gave us this. Our skin friction coefficient. And then from our Blasius skin coefficient data, our theoretical data, it appears as this. So these appear to match up pretty well. Then for us to get our drag force, we're going to go over to reports, double click that, and then click on forces. Make sure it's in the x direction, and then plate is selected for the drag, and then when you click print, you'll get this. So we can see here that the total force is 0.00956 in newtons, which let me check my theoretical value. So for our theoretical value, it came out to 0.00874 newtons. So this is very close to what we got in our theoretical. Then when we load up our Blasius theoretical, you can see here for the shear stress, I loaded in the data. So we can see it matches up really well with the shear stress for our simulated results, almost perfectly. The thing I want to add to be able to show the theoretical Blasius value, we're going to want to put our results in a XY file. After using the formula for obtaining each theoretical value, and then you're going to go to here, have the file ready, click here, this will be the file, right, and then click plate, make sure the plate's selected, and then plot. Oh, not this one, this one. So this is our theoretical skin friction coefficient, plotted along with our results for the skin friction coefficient. As you can see, they line up pretty well, and that's it for the theoretical. You basically do the same for the shear stress. You just change this to wall shear stress, and then have it also set on plate, and then you load the file with your theoretical XY values. So in conclusion, we got our skin friction coefficient and along with the theoretical, the wall shear stress along with the theoretical graph, and also our drag force and the results. And then over here we got our velocity profiles and contours. So I set up the pressure contour option along with the velocity of the air in this plot here.